All right, recorded is rolling. Today is Tuesday, November 15th. What I have lined up for you guys today is you guys remember these chapter 9 puzzles? I know it's like before the hurricane, and I handed this page to you guys. I remember this stuff. Actually, no, you guys had this page out yesterday. Because remember on the back side was printed the lab I had you guys do? Right. So it's the same paper. Okay. So I think I assigned like 8 of these questions to you guys. And I bet that based on the notes that we've done so far, which you can here, I was using this as a checklist of problems to go through a bunch of ideas with you guys. Okay. I bet you can figure these out. So, I'm gonna have you guys in teams. Obviously, you guys are in teams today, and I'll just walk around, help you guys out. Make sure that you can do this independently. Now, the open notes in-class quiz on Thursday. Some of the questions here, I'll tell you exactly what's in the quiz. Right? Some of the questions are going to come off this page that we did, yesterday and last week. Right? Some of the questions are straight off this page right here. Right? And there are a couple of questions that, well, right here. You guys see this bowling ball with the putty and the bouncy ball, right? So this is going to show up on the quiz too, right? So let's talk this out because I really like this pair of questions. So it's got a bowling ball just sitting there, right? Sit there, rest. Right? We're gonna throw a couple of objects at it, right? Each with the same amount of momentum, so mass and velocity. Let's start with a piece of putty, right? So say the putty comes in with like 5 kg per second of momentum. Just like, okay. Now, guys, what kind of collision would that be called?
Inelastic.
Inelastic, because it's gonna stick to the bowling ball. Okay? And do you guys think the bowling ball plus the putty is gonna roll off together with 5 units of momentum? You guys think? Yeah, I mean, it would have to because momentum is conserved in the universe. If you take that total momentum and you divide by the combined mass, which would be like most of the bowling ball, but plus a little bit from the putty, right? You could get the speed of the two rolling off together, like the velocity, right? You do that, right? So let's take that as the ground case, right? You guys know that it's 5 units of momentum rolling off together in the sunset together, because momentum is conserved, right? And let's contrast that with a different type scenario. What if you have a bowling bouncy ball that bounces off the bowling ball, okay? And I gave some example numbers here. Say it comes in with the same momentum that the putty did, but this collision is probably a lot closer to elastic, right? Maybe in an ideal case, it might be perfectly elastic, but at least it's close to that end of the spectrum. Might have a coefficient of restitution closer to 1, maybe it's like 0.9 or something, right? Okay, well, boing, bounce off. Okay. Is that what you guys got for coefficient of restitution? If you had a bounce ball yesterday, do you guys get something like 0.7, 0.8, something like that? Probably about. Okay. That might be like this scenario, a lot more elastic. Let's say it comes out to these numbers. So let's say the ball rebounds with like 3/5 of the momentum, right, relative to the ground or something. Right? Does this bowling ball roll off with how many units of momentum does the bowling ball itself have rolling off to the right? And it's not 2. It's not 2 units of momentum. It's not 2 kg per second. It's how many? Who's gonna get this? Who's gonna get it? How many units of momentum does this bowling ball have rolling off to the right? It's not 2. 8. Yeah, Brian got it. 8 units of momentum, right? Because the fact that there's a direction change, right? If something bounces off something, if there's a direction change, okay? What I left off here was a negative sign, right? Because remember, momentum is a vector quantity, right? So really, this could be like somebody has to be negative. Let's say the 5 is negative, 3 is positive. So if you final minus initial, wouldn't that be 3 minus -5, right? Because what is 3 units of momentum minus -5 units of momentum? It's 8 units of momentum. So the impulse on this bouncy ball was like 8 units of momentum, which means that the impulse on the bowling ball was also 8 units of momentum, right? Okay. So the bowling ball is, so the bottom bowling ball compared to the top bowling ball, which bowling ball is rolling off faster to the right? This guy right here, right? The one that has the bounce ball rolling off it, right? Because the top one, the combined mass rolls off with like 5 units of momentum, but the bottom one, the bowling ball itself, rolls off with 8 units of momentum. So there's more momentum acting on a tiny bit less mass, right? Yeah. So the bowling ball on the bottom rolls off faster. Okay? I did a Kahoot with my last class. I may or may not do this with you guys. Probably not, but maybe. But you guys know your questions that we've been going over on the backside are all these conceptual questions. There's one question that involves like an apple falling, where it's number 11. The force of an apple hitting the ground. So it's a really similar concept. Let's see if I can dig up the notes from my last class for that. Here it is. Okay. So suppose there's an apple falling from a tree and it's going to hit the ground. What's the force of impact? Right? And I can tell you it's going to be more than the weight of the apple. Suppose you have like a bathroom scale down here. Maybe the apple weighs like, I'm just gonna make up crazy numbers. Let's say you have a crazy heavy apple. It's like 1 kilogram, which is like 10 newtons, which is way heavier than an apple would be. Let's just simple numbers, right? So this apple has a mass of 1 kilogram, weighs 10 newtons. Okay? And I can tell you that when it slams into the scale, it's going to read more than 2 newtons, but how much more? Well, it depends on a few things. It depends on how fast it's falling, which has something to do with how high it fell from. It has obviously to do with the mass of the apple. It has to do with the time of impact, right? And it also has to do with whether or not the apple bounces, which is why I'm bringing up this this problem at all, because it's kind of like this. Whether it sticks or bounces, is like different amounts of force, different amounts of momentum transfer. Okay? Guys, what do you think the scale is going to read more if the apple goes and sticks, or if the apple boing bounces off? What's going to read more force of impact? Bounce. Yeah, if it bounces off. Right? Because if it bounces off, there's a huge change of velocity, like almost double the change of velocity. See, suppose it's landing at like 10 meters per second. If it goes and sticks 10 to 0, guess what's the difference between 10 and 0? 10. Okay. What if it bounces off extremely elastically and it rebounds with like 8 meters per second? What's the difference between 10 down and 8 up? 18, right? Isn't it 8 minus negative 10? Because there's a direction change, right? Guys, don't forget about these are all velocity, vector quantities, right? 8 minus negative 10 is a change in 18 meters per second. Okay? Multiplied by the mass of the apple, now you have a huge impulse. And then, okay, so the time interval also matters, fraction of a second. So different types of impact. Hey, how about this? Sort of related to this one. Suppose you're in a building on the 3rd story and the building's on fire. You have no choice but to jump out the window. What would you rather land on? Would you rather land on like a hard sidewalk, or would you rather land on a trampoline? Trampoline, right? And that gets a little bit different part of this impulse formula, like the time interval, right? Because if you land on the sidewalk, you crash all at once. This will be a tiny fraction of a second, right? And if you have a very small time interval, here's a good comparison here, right? Small time interval, have a huge force. But if you can extend that time interval, or right, you like double the time interval, you'll have half the force. Is that right? Which would be a better way to land, right? Is that it? Right. You guys hear that? All right. So, like I told you guys, you guys got the rest of the class period to work on these. I do want to mention one of these. Number 7. You guys see number 79 with the billiards, right? Which is like in 2 dimensions. We haven't actually covered anything quite in 2 dimensions, so this is sort of a challenge problem. I will tell you guys that this is not going to show up on the quiz, number 79. So number 79 is not going to be on the quiz. But if we have a few spare minutes tomorrow, I might go over that one with you guys, because I can tell you what the principle is. And the principle is that the momentum is conserved in each direction. So along the x-axis and along the y-axis. Right? And then you could set up a conservation momentum that way. Right? But anyway, you guys got the class period to work on those circle problems right there. I'll walk around and help you guys out. Double check focus. If there's anything instruments in, I think I'll have a couple spare minutes today to slip in some last grades if you guys can do that. All right, so let me close this recording and walk around and help you guys out.